Satellites don't have eyes, yet they can track hurricanes in real time, measure wildfire heat through smoke, and map floods even when clouds cover the ground. So how do satellites see Earth? Are they taking pictures, or are they measuring physics? In this video, you'll learn how satellite imaging really works, the sensors, the orbits, why weather satellite images look different from high-resolution pictures, how infrared and water vapor imagery work, and how radar satellites and Lidar can see when sunlight and clouds fail. Against all oddities, Case File 003, Space and Science Mysteries Explained Like an Engineer. Here's the mystery: satellites see what humans can't. Here's the physics: they measure energy, reflected, emitted, or bounced back. When people say satellites see Earth, they usually imagine a camera taking a photo like a phone, but most satellite imagery starts as measurements, numbers, captured by sensors that detect energy. Here's the engineer definition: a satellite sensor measures energy in specific wavelengths. Visible light is energy. Infrared heat is energy. Radio waves are energy. The satellite doesn't understand what it's looking at. It records signals, and then software turns those signals into images and maps. There are three ways a sensor gets a usable signal. First, reflected sunlight. This is optical satellite imagery. The sun lights up Earth, and the sensor measures what reflects back. That's how you get many daytime, photo-like images. Second, emitted heat. Everything warm emits infrared radiation. Earth emits heat day and night, so infrared weather satellites can track cloud-top temperatures even when the sun is gone. Third, active sensing. Some satellites bring their own flashlight. Radar satellites transmit radio waves and measure the echo. That's why radar can work at night and often through clouds. Now, a crucial detail for searchable satellite imagery questions. Many satellite images are not true color. They're false color composites. That means the data from different bands is mapped into colors humans can see, specifically to highlight features like vegetation health, burn scars, moisture differences, or cloud height. Engineers also describe sensors using 4 resolutions. This is a key phrase people search: spatial resolution, how much ground one pixel represents; spectral resolution, how many wavelength bands you measure; temporal resolution, how often the satellite revisits; radiometric resolution, how precisely it measures brightness differences. And here's the part that explains 90% of confusion online: you can't maximize all 4 at once. Wide coverage usually means less detail. Higher detail often means smaller coverage and fewer revisits. Satellites are engineered trade-offs. Engineers note, if you remember one thing, remember this: every satellite is a trade. Design is deciding what you can't afford to miss. Quick checkpoint: satellites don't see, they measure energy. Images are measurements turned into maps. And sensor design is a trade between detail, coverage, and revisit speed. To understand weather satellite imagery versus high-resolution satellite imagery, you need orbits. 2 big categories dominate Earth observation: geostationary orbit, very far away, matching Earth's rotation, so the satellite stays over the same region. This is why geostationary weather satellites can provide frequent updates, because they keep staring at the same hemisphere. Low Earth orbit, much closer to Earth, moving fast, scanning the planet in strips. This is why many Earth science and mapping satellites capture more detail and cover the whole globe, because the Earth rotates under their path. If you've searched why do weather satellite images look blurry, this is a major reason. Weather satellites prioritize wide coverage and fast refresh. High-resolution mapping satellites prioritize detail and consistent measurement. Another orbit phrase people search: sun synchronous orbit. Many Earth science satellites cross a location at about the same local, solar, time. That keeps lighting consistent, which matters for tracking change over years. Engineers note, orbit is part of the instrument. For live weather, you choose staring. For global measurement, you choose sweeping. Orbit is a design decision, not background trivia. Let's break down how weather satellites see. Weather satellites use multiple bands. 3 big ones matter for most viewers. Visible imagery shows cloud structure in daylight. Infrared imagery measures temperature day or night. Water vapor imagery reveals atmospheric patterns aloft. Infrared is widely searched, so here's the clean explanation. Infrared weather imagery is a temperature map. Cold cloud tops often mean high cloud tops. High storm tops can indicate stronger convection, which can be relevant for severe storms. Now the confusing one, water vapor imagery. The satellite is not taking a photo of droplets. It measures radiation in wavelengths affected by water vapor, producing patterns tied to moisture and temperature structure at certain atmospheric levels. That's why it helps reveal upper-level flow and large-scale dynamics. Some modern weather satellites also track lightning activity across huge regions. Lightning trends can shift as storms intensify. It's another data layer, not a magic warning system. Quick checkpoint. Weather satellites measure the atmosphere in bands. Geostationary weather satellites deliver frequent updates. Infrared is temperature. Water vapor imagery helps show upper-level structure and motion. Here's a misconception. Weather forecasting is not just watching cloud videos. Forecasts rely on physics-based models, and models need accurate inputs. Polar orbit weather satellites provide global measurements that feed models. One of the most valuable measurement types is atmospheric sounding, estimating temperature and moisture by altitude. Forecast models need a 3D snapshot of the atmosphere, not just a flat image. Engineers note, pretty imagery helps humans. Calibrated measurements help equations. The best forecast data is accurate, stable, and global, even if it doesn't look cinematic. Now, let's talk about Earth observation satellites people search for. Landsat, Sentinel, Satellite Land Use, NDVI, Thermal Satellite Image. Earth science satellites often focus on consistent measurement over time, tracking forests, agriculture, urban growth, water, ice, and long-term change. A common search question is, what does 30-meter resolution mean? It means 1 pixel represents a 30 by 30 meter patch of ground. Great for land change, not for tiny objects. If you've seen TV enhance a pixel into a face, that's fiction, not physics. Multispectral imaging is another top search term. Multispectral sensors measure bands humans can't see, like near-infrared and shortwave infrared. Vegetation reflects near-infrared strongly while water absorbs it. That difference helps classify land cover and estimate vegetation health. NDVI is a widely searched term. NDVI compares near-infrared and red reflectance. Healthy plants tend to reflect more near-infrared and absorb more red. NDVI is not plant happiness. It's a reflectance pattern that correlates with plant vigor. Thermal infrared is also searched a lot. Thermal sensors measure emitted heat, supporting land surface temperature maps, urban heat islands, and wildfire hotspot detection. Again, measurement translated into a map. Quick checkpoint. Optical uses reflected sunlight. Multispectral adds invisible bands for materials and vegetation. Thermal measures emitted heat for temperature patterns and hotspots. Now the engineer's favorite, radar satellites. Search terms, radar satellite, SAR satellite, synthetic aperture radar, radar satellite flood map, InSAR, Radar is active sensing. The satellite transmits radio waves and measures the echo. Because radar doesn't rely on sunlight, it works day or night. And many radar wavelengths pass through clouds much better than visible light, making radar powerful for flood mapping and stormy regions. Radar imagery also confuses people because brightness doesn't behave like a normal photo. In radar, bright areas often mean strong echo return, often rough surfaces, buildings, or certain angles. Smooth water can appear dark because it reflects energy away from the satellite. Synthetic Aperture Radar, or SAR, is how many radar satellites get higher resolution. Instead of one huge antenna, SR uses motion. As the satellite moves, it combines many pulses over time to form a higher resolution image. It's like building a larger, virtual antenna using physics and math. Engineers note, radar images are geometry. Angle matters, roughness matters, orientation matters. Treat radar like a normal photo and you'll misread it. A classic radar use case: flood mapping. Floodwater can appear dark, especially next to brighter land, and radar can map flood extent even under clouds. Another major use: InSAR, radar interferometry. By comparing the phase of radar waves between satellite passes, scientists can measure tiny ground movement, sometimes millimeters, related to subsidence, volcano inflation, or earthquake deformation. It's not because radar sees movement visually. It's because wave phase contains distance information. Radar has limitations. Speckle noise is common. Terrain can distort images with layover and shadows. Urban areas can be extremely bright due to multiple reflections. Radar is powerful, but it demands careful interpretation. Quick checkpoint. Radar satellites transmit and receive echoes. They work at night and often through clouds. SAR uses motion for detail. InSAR can measure tiny ground movement. Satellites can also measure height and structure. Radar altimetry measures sea surface height by timing return pulses. That supports sea level monitoring and ocean dynamics. Scatterometry estimates ocean surface winds by measuring how wave roughness changes backscatter. It's not seeing wind. It's seeing the ocean surface respond to wind. Lidar uses laser pulses to measure distance with high precision, supporting ice elevation change and forest canopy structure mapping. Lidar is like a tape measure made of photons. Now, the spy satellite question. Searchable term. Spy satellites explained. In engineering terms, spy usually means higher performance goals and targeted tasking, collecting data over specific areas at specific times. The fundamentals are the same: sensors, orbits, and tradeoffs. The difference is performance targets and access to the products. Also, there are still physical limits. The atmosphere blurs. Clouds block optical sensors. Viewing angles distort. And casual claims online about extreme resolution are often exaggerated. Engineers note, the sensor is only half the story. The image you see is produced by calibration, correction, geolocation, and processing. The pipeline is part of the instrument. If you've ever asked, why do weather satellite images look blocky? It's because weather systems prioritize wide coverage and fast refresh, not tiny details. If you've ever asked, why does satellite imagery use weird colors? It's because false color maps measurements into colors that reveal patterns humans can interpret, especially when the key data is outside visible light. Satellites see by measuring energy. Weather satellites stare and measure atmospheric bands. Earth science satellites scan globally for consistent measurement. Radar adds night and clouds. Lidar and altimetry add height and structure. The mystery isn't that satellites have supervision. The mystery is that physics is measurable from orbit. Subscribe for clean, engineering-style science, mysteries explained with real tools, not movie logic. Next case file, radar interferometry, how satellites measure cities sinking by millimeters, and how earthquakes leave fingerprints you can see from space. Comment this. Which sensor surprised you most? Infrared radar or Lidar?